So we have already discussed about the first law and the second law. First law says that all planets move around the sun in an elliptical orbit, where sun being at one of the foci. Second law says that the line which joins the sun and the planet sweeps equal area in equal interval of time. And third law says that square of the time period of revolution of a planet around the sun is directly proportional to the cube of the mean distance of the planet from the sun. Let me explain this law to you. What does it mean? For example, what is the time period? What is the time period? Time period is the total time taken by planet to revolve around the sun. For example, if this is the orbit of any planet, let it be planet A, B, C, D, let it be planet Earth, planet any planet. This is planet Earth, A. Planet A. What the time taken by planet and sun is at one of the foci. Okay. The time taken by this planet to revolve around the sun. Okay, to complete one revolution around the sun, that will be called as time period. Time taken by the planet to revolve to complete one revolution around the sun is called as time period, right? What does this law says? This says that the time period required, the time period of a revolution or of a planet around the sun, the time taken by the planet to move around the sun or time taken by the sun to move around the sun, let it be t. Mathematically, it says that the t square of the time period. Now, I have told you that the time period is the time taken by planet to move around the sun, or it's the one revolution, time taken by planet to complete one revolution around the sun. Square of that time period is directly proportional to cube of the mean distance. Is directly proportional to the cube of the mean distance. Now, what is cube of the mean distance? Now, let me tell you, if it would have been a perfect circle, if the orbit would have been perfect circle, then the value of r, that is this distance between sun and the circumference, right? If it would have been a perfect circle, then the value of r would have been constant, right? But here it is not a perfect circle. So how to find out the value of this r? What we will tend to do, we will tend to find out the mean of all. Now, how can we calculate the mean? You know, how can we calculate the mean? There is a formula to calculate the mean. The formula to calculate the mean is summation of all the observation divided by the number of observation, right? Sum of all the observation divided by the number of observation. That's what you have done in the 8th class, that how to find out the mean. So here what it says, that let the mean distance, let R1, R2, R3, for example, I said let R1 plus R2 plus R3 plus divided by 4 is equal to R, or let the mean distance of the planet from the sun, be R. Then what does Kepler's law, how can you express it mathematically? It says that square of the time period, that is the time taken by the planet to move around the sun, is directly proportional to cube of the mean distance between the sun and the planet. This is the third law of Kepler. This is how we can put it mathematically. That is, T square is directly proportional to R cube. T square is directly proportional to R cube, or in order to remove the sign of proportionality, I will introduce a constant. And let the constant be K. Then I can say T square is K upon R cube, or K, that's constant, is equal to T square upon R cube. T square upon R cube. Right? Now, let me once again explain it to you so that you will now have a quite clear that what Kepler said. This is the, that planets, all the first law of Kepler say that all the planets move around the sun in an elliptical orbit and sun being at one of the foci. Now, time period, that's time taken by the planet to move around the sun. Let it be T. Let the time taken by the planet to move around the sun be T. And this T is separate for all the planets. It is not same. Some days, for example, Earth take nearly 365 days and 6 hours. And some other planets take the time taken by the planet to move around the sun is not same. Like Mercury do the revolution in nearly 24 days or something like that. So every planet has a particular time period. For example, and this law is not only applicable to Earth, it's applicable to each and every planet which surround the sun. Okay, so I said that what Kepler said that this time period is the time taken by the planet to move around the sun, and the distance between the sun and the planet is not same. It's different everywhere. So how can we get you can say, how can we get the average value of the distance between the sun and the planet? For that, we will find out the mean of the distance between the sun and the planet. And you know how to calculate the mean. Mean means summation of all the observation divided by the number of observation in order to get. And let the mean distance between the sun and any planet be equal to R. Let me tell you that time period changes with the planet. It's not constant for all the planet. Every planet has its own time period. And even every planet has its own average mean distance from the sun. Because Mercury, if we see the orbit of Mercury, it's quite small. But if we compare it with the Earth's orbit, it is quite small, and Earth's orbit is the bigger one. And if we compare the Earth's orbit with the Pluto, that's quite big. You can say the orbit of the Pluto is very, very large. So this distance is also not same. It is for a particular planet. So constant which we are calculating will be different for different planet, but the observations will be same. That what Kepler said was that square of the time period. What's the time period? It is the time taken by the planet to move around the sun is directly proportional to cube of the mean distance between the planet and the sun. Cube of the mean distance between the planet and the sun. And I have told you, let the mean distance between the planet and the sun be R. So T square, that is The square of the time period is directly proportional to cube of the mean distance between the planet and the sun. And in order to remove the sign of proportionality, we have to introduce a constant. That would be constant r cube. And this constant will vary as the distance between the planets and the sun vary, or as the time period of the planet and the sun vary, this constant will be also vary. So we can say t square upon r cube is equal to constant, but for a particular planet, its value will be same. For Earth, its value will be same, but for if I compare this constant of Earth and some other planet like Pluto, some other planet like Mercury, some other planet like Venus, this will not have the same value. Like for G, universal for G, that is gravitational constant, universal gravitational constant, the value is 6.67 into 10 raised power minus 11. That is constant for whole universe. But the value of this constant is not it. The value of this will depend upon the time period of the planet and the cube of the mean distance between the planet. Right? So this was the third law of planetary motion. Okay. Now next topic which I am going to discuss about is Newton's second law and third law. How is. Now the question arises that how is it that what is inverse square rule which is used by Newton in postulating his famous universal law of gravitation. As I've told you that Newton's gravitational law was that you can say that what was the Newton's gravitational law? It says that every object in this universe attract each other with a force that is directly proportional to product of the masses and inversely proportional to square of the distance between the two. It says that if there are two balls, let it be A and B, it will be F is directly proportional to mass, product of the mass, and but inversely proportional to square of the distance between the two. How is it possible that how Newton was able to conclude about it? That it is the square of the distance, right? How Newton was able to conclude about it? He has concluded about that F is inversely proportional to r square just by using the Kepler's law of planetary motion. Now let me explain it. That is called as inverse square rule, which was used by Newton in forming the universal law of gravitation. Okay. 2 minutes. Okay, so we are here to prove the inverse square rule. Inverse square rule, which was used by Newton in framing the first universal law of gravitation, in which he said that force, the gravitational force existing between the gravitational force experienced by the two object is inversely proportional. Is the first observation that it is equal to the product of the masses, but it is inversely proportional to the square of the distance between the two objects. Now, how he was able to conclude about that it is inversely proportional to square of the distance between the two objects? Why he said, how he was able to convince himself and everyone that F is inversely proportional to square of the distance between the two. It was just by this inverse square rule. Now, how he was able to conclude about it, let me explain it to you. Let there be a planet R, any planet, which is moving around the sun in an elliptical orbit. This is as per the Kepler that if the sun, when a planet moves with a velocity, okay, this is as per the Kepler that when a planet moves around the sun, it moves in an elliptical orbit, right? And Newton used the third law to explain Kepler that how gravity weakened. As I told you that as the distance increases, so what will happen to the gravitational force? It will decrease. And as the distance decreases between the sun and the planet, it will increase and the velocity will change. So when a planet moves with the velocity v in a circular orbit of radius r, the force acting on the planet. So for that, as for the Kepler, the velocity will not remain the same. So what Newton said, he said that consider, in order to reach to the inverse square rule, he said consider that the planet is moving around the sun not in an elliptical orbit but in a perfect circle. Okay. So that the velocity will remain constant. Velocity, let the planet move with velocity v. So when a planet moves with the velocity v in a circular orbit of radius r, because being a perfect circle, the value of the radius will be r every time. Now the force of gravity, the force between the planet and the sun, the force acting on the orbiting planet is equal to, force is directly proportional to v square upon r. Alright? Where v is the velocity with which the planet is moving around the sun and r is the distance between the sun and the planet. Okay. So the force which is present between the two is directly proportional to v square upon r. Right? Let time taken by the planet to move around the sun be equal to t. The time taken by the planet to move around the sun is t. Then how can we calculate the velocity? You know, velocity is equal to, when the object is moving around the circular object, when a object is moving around the circular path, then velocity is equal to distance upon time taken. How can we calculate the distance? It will be 2 pi r, and time taken by the planet to move around the sun be t, so it is upon t. So velocity is 2 pi r upon t. I once again say that let v be the velocity with which the object is revolving around the sun. Okay. Let time taken by the sun to revolve around the sun be t. Let time taken by the planet to move around the sun be t. The distance between, because Newton said that consider it is a perfect circle, then the value of r will be same. That is, the radius is the between the sun and the planet. Let it be r. Okay. Then the force which experience, then the force acting on the orbiting planet, then the force which acts on the orbiting planet is equal to square of the velocity upon the radius. Okay. Then how can we calculate? If the object is moving along a circular path, we know velocity is equal to distance traveled upon time taken. It being a circular path, its distance is 2 pi r upon t, right? So I can, now what is the constant? Constant is 2 and pi. As the planet will change, the r and t will change. As the distance, if we talk about different planets, if we talk about the different planets, the value of r and t will change as per the planet. All right. But what will not change here, the value is 2 and pi. If I scrape this 2 and pi, then this equivalent sign will be changing into proportional. I once again say, in order to change the sign of proportionality, what we introduce is a constant. जब हमें साइन ऑफ प्रोपोर्शनैलिटी को हटा के कांस्टेंट तो हम इक्विवेलेंट करना होता है, तो उस टाइम पे हम what we introduce is a constant. But now what I am tending to do is that once I scrape out this constant, अगर मैं इस constant को निकाल देते हैं तो it will, the sign of equality will get changed into proportionality, right? So we can write it like this, that once I remove this, because आपने कई बार देखा होगा, in order to remove the sign of proportionality and change it into equivalent sign, we are introducing a constant. Let it be k, let it be t, let it be something else. Now if we scrap this constant, then it can change back into proportionality. That is what I have done in this step. I have scraped the 2 pi so that it will get converted into proportionality. Instead of equivalent sign, now there will be the sign of proportionality. Now squaring both the sides. Square both the sides. So our value will be v square is directly proportional to r square upon t square. Am I right? Okay. R square upon t square. This is how it will work. Squaring both the sides, you will get v square is directly proportional to r square upon t square. Right? Now, what I will do, I will write it like this, that multiply, okay, because the board is quite small, so yes, let me use the other side of the board. So it was v square is directly proportional to r square upon t square once I have squared both the sides. This was the value which I got it. Okay. Now what I'm trying to do, multiply as well as divide by r on left hand side. Multiply as well as divide by r on left hand side. It will have no effect on our, this is r square multiply by r and t square divide by r also, right? Now in mathematics, you know, when anything raised to power 0 is 1, and when the bases are same, powers are to be added. So our equation can be like this, that r cube upon r into t square into t square, right? But you know, as per, so v square is directly proportional to r cube upon t square into r. Can I write it like this? Okay. But you know, as per Kepler's law, r cube upon t square is a constant. R cube upon t square is a constant. So it will be v square. We will scrape this and it is inversely proportional to 1 upon r. 1 upon r. Okay. 1 upon r. Now substituting the value of v square in this equation. In this equation, that is F is directly proportional to V square upon R. What is our V square equal to? Our V square is equal to 1 upon R. V square is directly proportional to 1 upon R or V square. So now substituting the value of